what if you looked back at a photograph from the moment of your birth and saw not an infant, but a fully grown adult? This is the paradox facing us tonight. The James Webb Space Telescope, our golden eye in the dark, has peered back to the dawn of time and has seen something that should not exist. It has found galaxies in the cradle of the universe that are impossibly large, impossibly bright, impossibly mature. Tonight, we are not here to solve this mystery. We are here to drift within it, to let its immense, quiet questions rock us into a state of peaceful wonder. Let go of the day, let go of the noise, and join me on a journey to the edge of time, where the universe is revealing a story far stranger and more beautiful than we ever imagined. A story that is just beginning to unfold. Before we travel 13 billion years into the past, let us first understand the map we thought we knew. For decades, our story of the cosmos had a clear and logical beginning. After the Big Bang, the universe was a hot, dense, and uniform fog of particles. As it expanded and cooled, gravity began its slow, patient work. It was a gentle sculptor. It pulled together wisps of hydrogen and helium gas like a shepherd gathering a flock. Over hundreds of millions of years, these small clouds were meant to merge, growing larger and larger. They would form the first small stars, then modest star clusters, and eventually, after an immense stretch of time, these would combine to form the first small, infant galaxies. Our theories, our computer simulations, all painted this picture of gradual, steady growth. The universe was a slow bloomer. The first billion years were supposed to be its quiet childhood, a time of small things slowly becoming large. This was the standard model of cosmology, a comfortable, elegant story that made sense. And it is this very story that the Webb telescope is now asking us to reconsider, to perhaps rewrite entirely. Imagine yourself floating in the profound silence of space. Before you hangs the James Webb Space Telescope. It is not a tube like the telescopes of old. Instead, it is a magnificent golden honeycomb. 18 hexagonal mirrors, polished to a perfection beyond human touch, fit together to form one giant, light-gathering surface. It is shielded from the sun by a vast, 5-layered kite of silvery material, keeping it in a perpetual, cryogenic twilight. This telescope is more than a machine of glass and metal. It is a time machine. Its primary purpose is not to look out, but to look back to a time so distant that its light is only now reaching us. Every photon it collects is a ghost, a messenger from an almost forgotten epoch. The deeper it looks into space, the further it sees into the past. It is designed to capture the faintest, oldest whispers of light from the very first stars and galaxies, an era we call the cosmic dawn. As we begin our journey, picture this golden eye drifting silently 1,000,000 miles from Earth, turning its gaze towards a tiny, seemingly empty patch of the night sky, ready to receive messages that have been traveling towards us since the beginning of everything. It waits with inhuman patience in the cold and the dark for the first stories of the universe to arrive. The light that Webb seeks is not the kind our eyes can see. It is ancient and tired. For over 13 billion years, it has journeyed across an expanding universe, And as the fabric of space-time itself has stretched, so too has this light. Its waves have been pulled, elongated, shifted towards the red end of the spectrum and beyond, into the infrared. This is why Webb's mirrors are coated in a microscopically thin layer of gold. Gold is exceptionally good at reflecting infrared light. So, the telescope is not just a time machine. It is a specialized instrument, tuned to a specific frequency of the past. It listens for the colors of creation. The program tasked with this profound search is known as JIDES, which stands for the James Webb Advanced Deep Extragalactic Survey. The name itself sounds like a quest from an ancient myth. The JADES team pointed the telescope at a small region of the sky, a patch so small it could be covered by a grain of sand, held at arm's length. This is the concept of a deep field. Stare at nothing long enough, and the universe will fill the void. For hundreds of hours, Webb's mirrors drank in the faint, infrared glow from this sliver of darkness, accumulating photons one by one, building an image from whispers and echoes. Let the concept of the cosmic dawn wash over you. Try to visualize it. After the initial flash of the Big Bang, the universe entered a period known as the Dark Ages. There were no stars, no galaxies. There was only a vast, expanding ocean of neutral hydrogen and helium gas drifting in darkness. It was a silent, simple, and profoundly empty place. The cosmic dawn is the moment this darkness ended. It is the period when the very first stars ignited, like tiny candles in a colossal, dark room. Their ultraviolet light began to ionize the surrounding gas, burning away the primordial fog. This was the universe's first sunrise, a process that took hundreds of millions of years. According to our established models, this dawn should have been gentle. The first galaxies were expected to be small, wispy, and irregular. They would be faint collections of the first generation of stars, known as population 3 stars. These were theoretical behemoths made of pure hydrogen and helium, burning hot and fast before exploding and seeding the cosmos with the first heavy elements. Webb was built to find these faint, first whispers of light, these small, infant galaxies. It was searching for the cosmic equivalent of a newborn's first cry. The data from the JADES program began to stream back to Earth. Imagine the quiet hum of servers in a control room. Scientists, a mix of excitement and nervous anticipation, watched as the raw data was processed. The information gathered by Webb was translated into images, into spectra, into numbers. And as the first images of this deep field resolved on their screens, they saw what they expected, and so much more. The image was jeweled with distant galaxies, thousands of them, each a faint smudge of reddish light. The further away a galaxy is, the more its light is redshifted. By measuring this redshift, astronomers can calculate its distance and, therefore, its age. They began to identify the most distant candidates, the ones with the highest redshifts, the ones that existed just a few 100 million years after the Big Bang. These were the ghosts they were hunting, the denizens of the cosmic dawn. But as they looked closer at a handful of these ancient objects, a quiet confusion began to ripple through the team. Something was wrong. These weren't the small, faint, infant galaxies they had predicted. Among the faint red dots in the JIDES deep field, A few stood out. They were exceptionally bright. When the astronomers calculated their properties, the numbers didn't seem to add up. Take, for example, a galaxy now cataloged as Jades GS 13-0. The Z13 in its name refers to its redshift, placing it at a time just 320 million years after the Big Bang. The universe was only 2% of its current age. At this epoch, this galaxy should have been a tiny protogalaxy, a mere seed of what it would become. Yet the data showed something else entirely. It was already a substantial galaxy, containing hundreds of millions of stars. It was a beacon in the primordial dark, shining with the light of a mature star system. And it wasn't alone. Webb found several others from this same early period, all surprisingly massive and luminous. The scientists initially suspected errors. Could their instruments be miscalibrated? Could they be misinterpreting the redshift? Could these objects be closer, less remarkable galaxies masquerading as ancient pioneers? They checked and rechecked their data with meticulous care, but the numbers held firm. The observations were robust. The universe, in its infancy, had somehow managed to build galaxies that, by all rights, should have taken 1 billion years or more to form. Let's try to grasp the scale of this impossibility. Imagine you are tasked with building a skyscraper. You are given a small pile of bricks and told you have only 1 hour to complete the job. It's a ludicrous task. You simply don't have enough material or enough time. This is the problem presented by these early galaxies. The material for building galaxies is gas, primarily hydrogen. In the early universe, this gas was spread out very thinly. Gravity, the cosmic construction worker, had to pull this gas together into dense enough clumps to ignite star formation. This process takes time. Furthermore, the amount of available gas within any given region of space was limited. Our standard model, known as lambda CDUM, which includes dark matter and dark energy, provides a very specific recipe for the universe. It dictates how quickly structure can form. It sets a cosmic speed limit. These massive early galaxies appear to be breaking this speed limit. They seem to have gathered more material and converted it into stars far more efficiently and rapidly than our best cosmological model allows. It's as if the universe skipped its childhood and adolescence and jumped straight into adulthood. This is not a minor discrepancy. It's a fundamental challenge to our understanding of how everything we see came to be. The mystery deepens when we consider not just their mass, but their brightness. These galaxies are not just heavyweights. They are shining with an intensity that is difficult to explain. A galaxy's brightness comes from its stars. To be this luminous, these early galaxies must have been forming stars at a furious rate, a pace far exceeding what we see in most galaxies today, even our own Milky Way. This frantic star formation is known as a starburst, but a starburst needs a tremendous amount of fuel, cold, dense gas. Where did all this fuel come from so early in the universe's history? How did it accumulate in one place so quickly? This leads us to a fascinating and beautiful possibility. Perhaps the very first stars were different. Perhaps the stars that populated these first galaxies were not like our sun. They might have been the legendary population 3 stars, forged from the pure, pristine hydrogen and helium of the Big Bang. without heavier elements to help them cool and fragment. The gas clouds that formed them would have been massive, leading to the birth of stars hundreds of times more massive than our sun. These giants would have been incredibly hot and luminous, burning through their fuel in a mere 1 or 2 million years before exploding as brilliant supernova. If these early galaxies were packed with such stellar behemoths, it could explain their extraordinary brightness. So, are we seeing the light of these mythical first stars? It is a tantalizing thought. The signature of population 3 stars should be unique because they contain no metals, the term astronomers use for any element heavier than hydrogen and helium. Their light spectrum would be very distinct. Webb's instruments are sensitive enough to hunt for these spectral fingerprints. The current evidence is still being debated. Some analyses of the light from these galaxies suggest the presence of stars that are indeed very low in metals, consistent with what we'd expect from this early generation. However, there is no definitive smoking gun evidence yet. The mystery might be even more complex. An alternative, and perhaps more unsettling, explanation for the intense brightness could lie not with the stars, but with what sits at the center of these galaxies. It is possible that they are being powered by supermassive black holes. A black hole itself emits no light, but as it greedily pulls in the surrounding gas and dust, this material forms a swirling, superheated accretion disk that can outshine all the stars in the galaxy combined. This would make the galaxy an active galactic nucleus, or a quasar. But this solution only deepens the paradox. How could a supermassive black hole, millions or even billions of times the mass of our sun, form so quickly after the Big Bang? This brings us to the quiet, invisible architect of the cosmos, dark matter. According to our standard model, dark matter is the scaffolding upon which all visible structure is built. It is a mysterious, unseen substance that makes up about 85% of the matter in the universe. It does not interact with light, but it does interact with gravity. Long before the first stars ignited, vast, invisible halos of dark matter were already beginning to collapse under their own weight. These dark matter halos acted as gravitational wells, cosmic potholes into which ordinary matter, the hydrogen and helium gas, would fall. Once trapped in these wells, the gas could become dense enough to form stars and galaxies. The standard theory predicts a hierarchical formation. Small dark matter halos form first, and then merge over eons to create larger and larger halos, capable of hosting massive galaxies like our own. The existence of these impossible early galaxies suggests that this process might have been far more efficient than we believed. Perhaps the dark matter halos in the early universe grew much faster or were much denser, creating gravitational wells so deep that they could funnel in enormous quantities of gas at an astonishing rate. We are not just questioning the formation of stars. We are questioning the very nature and behavior of the invisible skeleton of our universe. The surprising discoveries force us to open our minds to new and beautiful cosmic possibilities. We must be willing to question our most fundamental assumptions. One such assumption is the nature of the seeds from which large structures grew. The standard model assumes that after the Big Bang, the universe was almost perfectly smooth, with only tiny quantum fluctuations in density. These minuscule variations were the seeds that gravity later amplified. But what if the seeds were bigger? Some theories propose the existence of primordial black holes that did not form from collapsing stars, but were instead forged in the immense pressures of the first second of the universe's existence. If such black holes existed, and if they were massive enough, they could have acted as gravitational anchors from the very beginning. Instead of waiting for dark matter halos to form slowly, galaxies could have begun to grow immediately around these pre-existing massive seeds. This black hole first model turns the standard picture on its head. It suggests that supermassive black holes are not the result of galaxy evolution. They are the cause of it. They are the cosmic eggs from which galaxies hatched. It's a profound shift in perspective, suggesting the monsters in the dark were actually the midwives of creation. Let's drift with this idea for a moment. Picture the young universe, a vast, dark canvas. In the standard model, this canvas is slowly populated by countless small points of light that gradually merge and grow. But in this black hole first scenario, the canvas begins with a few scattered points of immense gravity. These are the primordial, supermassive black holes. They are invisible, but their presence warps the space around them. The primordial soup of hydrogen and helium gas, instead of clumping randomly, is drawn inexorably towards these gravitational anchors. The gas streams across the cosmos, forming vast filaments that all lead to these central points. Where the gas converges, it becomes dense, it cools, and it ignites in a furious burst of star formation. The galaxy does not build its black hole. The black hole builds the galaxy. This could explain both the immense mass and the startling brightness of the galaxies Webb has found. They are massive because they were seeded by a massive object. They are bright because the black hole is feeding voraciously on the infalling gas, creating a brilliant quasar at their heart. It paints a picture of a more dramatic, more top-down creation story, driven by enigmatic objects born in the universe's first fiery moments. Could our understanding of the universe itself be incomplete? Beyond the mysteries of galaxy formation, these discoveries push us to reconsider the very laws that govern the cosmos on its largest scales. Our current model is called Lambda CDM. Lambda represents dark energy, the mysterious force causing the expansion of the universe to accelerate. CDM stands for cold, dark matter, the slow-moving, invisible substance we discussed. This model has been incredibly successful at explaining a vast range of cosmic observations, from the cosmic microwave background radiation to the large-scale distribution of galaxies. But it is not perfect, and these early massive galaxies are one of its most significant challenges to date. Perhaps dark matter isn't entirely cold and slow-moving. Perhaps it has properties we haven't yet discovered that allowed it to clump together more rapidly in the early universe. Or maybe the nature of dark energy, the lambda part of the equation, was different in the past. Some theories suggest a period of early dark energy that briefly accelerated the universe's growth, giving gravity a head start. We are in a realm of deep speculation, but it is speculation driven by real, hard data. we are being invited by the universe to think more deeply, to imagine a cosmos with a richer, more complex history than the one we have written so far. Let us take a moment to appreciate the tool that makes this all possible. The James Webb Space Telescope is an oracle, but its pronouncements are not spoken in words. They are written in light. Specifically, they are written in spectra. When Webb captures the light from a distant galaxy, it doesn't just take a pretty picture. Its instruments, like in NIRSpec, act like prisms, spreading that faint light out into its constituent colors, or wavelengths. This rainbow of light is a galaxy's fingerprint. Within it are dark lines, called absorption lines, and bright lines, called emission lines. These lines are created by different chemical elements, which absorb or emit light at very specific wavelengths. By studying these lines, astronomers can learn an incredible amount. They can determine the galaxy's chemical composition, how many heavy elements it contains. They can measure its temperature and density. And most importantly, they can precisely measure its redshift. They can see how much the known patterns of, say, hydrogen have been stretched towards the red. This spectroscopic data is what turns a pretty picture into a revolutionary scientific discovery. It is what confirms, beyond a doubt, that these galaxies are not nearby objects, but are truly ancient relics from the dawn of time. It is the hard evidence that grounds our soaring cosmological dreams. So, where do we go from here? This is not the end of a story, but the beginning of 1,000 new ones. The discovery of these universe breakers, as some have nicknamed them, has ignited a firestorm of activity in the astronomical community. Theorists are scrambling back to their blackboards and supercomputers, trying to tweak the lambda CDM model, or develop new ones that can accommodate these massive early bloomers. They are exploring all the possibilities we have touched upon. More efficient dark matter, primordial black hole seeds, different types of early stars, and even modifications to our understanding of gravity itself. Meanwhile, observers using Webb are planning even deeper surveys. They will hunt for more of these enigmatic galaxies to see if they are rare oddballs or a common feature of the early universe. They will use the telescope's powerful spectrographs to dissect their light in even greater detail, searching for clues about the nature of their stars and the black holes at their centers. Science is a conversation between theory and observation. Right now, observation has just spoken, and it has said something completely unexpected. The coming years will be filled with the quiet, careful work of listening to that statement and formulating a reply. It is a time of profound and wonderful uncertainty. Let's put the timeline into a more human perspective to feel the depth of the time we are exploring. Imagine the entire 13.8 billion year history of the universe is compressed into a single calendar year. The Big Bang happens at the first second of January 1st. On this scale, our own galaxy, the Milky Way, doesn't form until early May. Our solar system and the Earth appear in early September. The dinosaurs roam the Earth in the last week of December. And all of recorded human history, every king and queen, every empire, every discovery, occupies only the final 10 seconds before midnight on December 31st. The galaxies that Webb has discovered, these impossible structures, existed in the first week of January. They are from a time when the universe was just a newborn. Seeing a fully formed, massive galaxy in the first week of January is like seeing a fully grown oak tree sprout from an acorn in a single day. It disrupts our sense of natural timing, of gradual growth. It forces us to confront the idea that the cosmic processes we thought were slow and patient might have had a much more dramatic, rapid, and violent opening act. We are reading the first page of the universe's diary, and it is nothing like the preface we had written. What would it be like to witness this era firsthand? Let your mind drift there. Imagine floating in the void, 300 million years after the Big Bang. The universe around you is not the empty, dark place it is today. The space between galaxies is much smaller. The primordial fog of hydrogen has not yet been fully cleared. You would be surrounded by a cosmic haze, and through this haze, you would see the first galaxies. They would not be the grand, majestic spirals like Andromeda or the Milky Way. They would be compact, intensely bright, and chaotic knots of blue-white light. They would be blazing with the light of gargantuan population 3 stars. Stars so bright, they would make the most brilliant stars in our own sky look like dim embers. The rate of supernova explosions would be staggering. The galaxies would flicker and pulse with the constant death of these stellar giants, which seed the surrounding space with the first heavy elements. And at the heart of the most massive of these galaxies, you might see the brilliant, piercing light of a quasar, a beacon signifying the rapid growth of a supermassive black hole. It would be a violent, creative, and incandescently beautiful epic, a cosmic forge operating at full blast, laying the foundations for everything that was to come. The challenge these galaxies pose is a beautiful one. It reminds us of a fundamental truth about science. Science is not a collection of immutable facts written in a stone textbook. It is a living, breathing process of discovery. It is a journey of successive approximations, of getting less wrong over time. For a scientist, an observation that perfectly matches a theory is satisfying, but an observation that breaks a theory, that is exciting. That is where the real progress happens. A paradox like this is a gift from the universe. It is a signpost pointing towards a deeper, more elegant truth that we have not yet grasped. It tells us that our map of reality is incomplete, that there are entire continents of knowledge waiting to be discovered. The men and women who study these Jada's galaxies are not distressed or discouraged. They are thrilled. They are like explorers who have found a new world that does not appear on any of their charts. The work of redrawing the map has begun, and it is the greatest adventure of all. It is a testament to human curiosity that we can build a golden eye to stare at the dawn of time, and a testament to our humility that we are willing to admit we do not understand what we see. This entire discovery hinges on our ability to measure cosmic distance, a concept that is itself beautifully counterintuitive. In our daily lives, we measure distance with rulers or lasers. In space, we measure it with time. The further away something is, the longer its light is taken to reach us. The redshift of a galaxy is our cosmic ruler. When we say a galaxy has a redshift of 13, we are saying that the universe has expanded by a factor of 14 since that light was emitted. The light waves themselves have been stretched to 14 times their original length. It is a direct measurement of the expansion of space itself. This is why astronomers have such confidence in these distances. But could there be something we are missing? A few fringe theories have suggested that perhaps redshift is not entirely due to expansion. Could there be some other, unknown physical process that can redden light over vast distances? An effect of tired light? While these theories are not widely accepted, as they fail to explain many other cosmic observations, the new Webb data forces scientists to re-examine all possibilities, even the most unlikely ones. The universe has surprised us before, and it is a safe bet that it will surprise us again. For now, however, the evidence overwhelmingly points to one conclusion. These galaxies are truly as old and as puzzling as they seem. Let's consider the chemical implications of this discovery. Our bodies, the planet we live on, the air we breathe, all are made of heavy elements forged in the hearts of stars. Hydrogen, helium, and a tiny bit of lithium were created in the Big Bang. Every other element on the periodic table, the carbon in our cells, the oxygen we breathe, the iron in our blood, is the product of stellar nucleosynthesis. It was cooked inside stars and then scattered across space when those stars died. This process of cosmic enrichment was thought to be very slow. It would take many generations of stars, living and dying, to build up a significant reservoir of heavy elements. Yet, when Webb studies the spectra of some of these surprisingly mature early galaxies, it finds hints of elements like oxygen. The presence of oxygen, however small, just a few 100 million years after the Big Bang, is astonishing. It means that at least one generation of massive stars had already been born, lived out their short, brilliant lives, and exploded as supernova to enrich the gas from which a second generation of stars was forming. The cosmic recycling program started much earlier and worked much faster than we had ever dared to imagine. The universe was in a hurry to create the building blocks of planets and of life. This story is also a profound lesson in perspective. We look up at the night sky, and it seems serene, unchanging, eternal. We see patterns in the stars that have been watched by our ancestors for millennia, but this tranquility is an illusion of time. The universe is a dynamic, evolving entity, and its youth was a time of unimaginable change and speed. The Webb discoveries are a window into that frantic period. It's a reminder that our own existence is the result of a chain of events that began in that fiery, creative dawn. The very atoms in your body were forged in stars that were born because of processes set in motion in that first 500 million years. When we feel small and insignificant in the face of the cosmos, we can also remember that we are intrinsically connected to it. We are not just observers of the universe. We are a part of it. We are made of stardust, and the story of these first galaxies is the earliest chapter in our own cosmic ancestry. The paradox of their existence is, in a way, the paradox of our own. We are the improbable result of a universe that seems to be far more creative and efficient than it has any right to be. As we drift deeper into this cosmic mystery, let the questions themselves become a source of comfort. We do not need to have the answers. It is enough to simply hold the questions in our minds, to feel their weight and their beauty. How does the universe build so much, so fast? What is the true nature of the dark matter that guides its structure? Were there monsters, primordial black holes, hiding in the crib of the cosmos? Were the first stars truly the brilliant, short-lived giants of our theories? These are not questions with simple, textbook answers. They are koans given to us by the universe itself. They invite contemplation, not just calculation. They are a reminder that the world is more complex, more surprising, and more magical than our models can ever fully capture. There is a deep peace to be found in accepting this uncertainty. It is the peace of knowing that there will always be more to discover. Always another layer of the cosmic onion to peel back. The journey of understanding is infinite, and tonight we are simply resting at a beautiful, new, and unexpected vista along the way. Consider the name of our own galaxy, the Milky Way. It is a gentle, poetic name, evoking a soft band of light spilled across the night sky. Our galaxy is a mature, relatively calm place. Star formation happens at a slow and steady pace, but it was not always this way. The Milky Way itself was built from smaller pieces. Over billions of years, it has merged with and cannibalized hundreds of smaller dwarf galaxies. The evidence of this history is still visible in the form of stellar streams, rivers of stars that arc across our galactic halo, the ghostly remains of past collisions. Perhaps the impossible galaxies seen by Webb are the ancestors of galaxies like our own. Perhaps we are looking at the great-grandparents of the Milky Way. They were the frantic, chaotic starbursts whose descendants would eventually settle down, merge, and organize themselves into the graceful spiral we call home. Seeing them in their youth is like looking at an old family album and finding a picture of a revered ancestor as a wild, rebellious teenager. It adds a new dimension to their character, a new depth to their story. It connects our calm cosmic present to a turbulent and brilliant past. The implications of this discovery ripple outwards, touching other great mysteries of astronomy. One of these is the question of Ryanization. As we mentioned, after the Big Bang, the universe was filled with a fog of neutral hydrogen gas. The light from the first stars and galaxies was responsible for clearing this fog, a process called reionization. For decades, astronomers have debated what exactly provided enough energetic light to do this. The leading candidates were small, numerous dwarf galaxies. But models have always struggled to explain how these faint galaxies could produce enough radiation to ionize the entire universe. The discovery of these massive, incredibly luminous early galaxies offers a new potential solution. Perhaps it wasn't a death by 1,000 cuts from countless dwarf galaxies. Perhaps it was a much faster, more dramatic process, driven by a smaller number of these intensely powerful universe breakers. Their brilliant stars, and potentially the quasars at their cores, would have pumped enormous amounts of ionizing radiation into the surrounding space, burning away the cosmic fog far more rapidly and efficiently than we previously thought. These galaxies didn't just build themselves quickly. They may have reshaped their entire cosmic environment, making the universe transparent and paving the way for the cosmos we see today. It is also worth noting the sheer technological marvel that allows us this glimpse into the past. The Webb telescope is operating at a temperature of minus 388 degrees Fahrenheit, or about 40 Kelvin. It needs to be this cold so that its own faint heat does not interfere with the ancient infrared light it is trying to detect. Its mirrors are so smooth that if you were to scale one of them up to the size of the United States, the largest imperfection would be only a few inches high. It is held in a stable position in space, not by orbiting the Earth, but by orbiting a gravitationally stable point 1,000,000 miles away, known as the second Lagrange point, or L2. At this point, it can keep its back to the Sun, Earth, and Moon simultaneously, allowing its sun shield to protect it from their light and heat. Every image it produces is the result of decades of work by thousands of engineers and scientists. It is a monument to human ingenuity and our unquenchable desire to know where we came from. When we look at these images of impossible galaxies, we are not just seeing the dawn of the universe. We are seeing the pinnacle of human collaboration and curiosity. Let's think about the shape and form of these cosmic pioneers. We are used to seeing breathtaking images from the Hubble telescope of nearby galaxies in all their intricate glory. We see grand spiral arms, glowing pink nebulae, and dark dust lanes. The early galaxies discovered by Webb look nothing like this. In the telescope's images, they are often just small, reddish, and somewhat clumpy smudges. They lack the organized structure of mature galaxies. They are not yet settled into a calm, rotating disk. They are messy, chaotic, and still in the process of assembly. Astronomers describe some of them as looking like clumps on a string, or train wrecks. This is exactly what we would expect from a galaxy undergoing rapid, violent star formation and frequent mergers with its neighbors. Their beauty is not in their elegance, but in their raw, untamed power. They are a snapshot of creation in its most primordial and energetic phase. They are the sketch, not the finished painting. And in that raw form, they hold the secrets of how the magnificent cosmic structures we see today first came into being. They are beautiful because they are real and because they are a mystery. The search for life in the universe is inextricably linked to the story of galaxy formation. Life as we know it requires heavy elements. It requires planets. And planets form from the leftover material in the disks around young stars. The faster a galaxy can produce and distribute heavy elements, the sooner the conditions for planet formation and potentially life can arise. The discovery that the universe was producing these elements and building large galaxies so much earlier than expected has a subtle but profound implication for astrobiology. It could mean that the window of opportunity for life to begin opened much earlier in the universe's history than we thought. While this does not mean that life existed back then, it means the necessary ingredients were in place. The universe may have been habitable, at least in principle, for billions of years longer than our previous models suggested. It expands the cosmic stage, both in space and in time, on which the story of life could have unfolded. It is a quiet, hopeful whisper from the dawn of time, suggesting that the universe has been pregnant with possibility for almost its entire existence. There is a beautiful duality in this story. On the one hand, these discoveries highlight the immense, unimaginable scale of the cosmos. We are talking about objects whose light has traveled for over 13 billion years to reach us. Structures containing hundreds of millions of stars, existing in a time so remote it is difficult for the human mind to grasp. It is a story of magnificent grandeur. On the other hand, the key to unlocking this story lies in the tiniest, most subtle clues. It lies in the precise wavelength of a single photon. It lies in the faint spectral line of an oxygen atom. It lies in the careful analysis of data, the patient checking and rechecking of numbers. It is a reminder that the grandest truths of the universe are often hidden in the smallest details. To understand the whole, we must first understand its parts. The vast and the infinitesimal are woven together. The story of the cosmos is written in a language of both supernova and subatomic particles, and our task is to learn how to read it. As you drift off to sleep, you can appreciate this wonderful balance, the dance between the immense and the intricate that defines our universe. This entire field of study is evolving in real time. The scientific papers announcing these discoveries are only a few years old. The data is still fresh. What we are talking about tonight is science in the making. There's no final consensus yet. Different teams of astronomers are analyzing the same data and sometimes coming to slightly different conclusions about the exact masses or ages of these galaxies. There are ongoing debates, friendly arguments, and a collective effort to make sense of this new information. This is how knowledge progresses. It is not a sudden flash of insight, but a slow, careful, and sometimes messy process of building a new understanding, brick by brick. By listening to this story, you are getting a glimpse behind the curtain into the real, living world of scientific inquiry. It is a world of wonder, of confusion, of excitement, and of a shared passion for understanding our place in the cosmos. You are on the front lines of cosmic discovery, where the map is still being drawn and "Here be dragons" might be written in the margins. Finally, let us return to the feeling of wonder. The universe does not owe us an explanation that is easy to understand. It does not have to conform to our models or our expectations. Its beauty lies in its capacity to surprise us, to challenge us, to invite us into a deeper and more profound state of not knowing. The existence of these impossible galaxies is not a failure of our science. It is its greatest triumph. It is a sign that our tools have become so powerful that we can now ask questions of the universe that we didn't even know we had. It is a humbling and exhilarating experience. It's a call to be more imaginative, more creative, and more open in our thinking. The universe is not just stranger than we imagine. It is stranger than we can imagine. And as you let your consciousness drift, as you let go of the day and sink into a deep and restful sleep, you can carry this feeling of gentle wonder with you. The wonder of a universe that is still revealing its secrets, one ancient photon at a time. The quiet joy of being alive in a time when we can witness the dawn of everything. So we find ourselves at the end of our journey tonight, floating in the quiet aftermath of a revelation. We have traveled to the edge of time, to an era just a few breaths after the Big Bang, and found giants in the cosmic nursery, we have seen galaxies blazing with the light of millions of stars that, according to our best stories, simply should not be there. This is the new, beautiful puzzle presented to us by the James Webb Space Telescope. It's a paradox that could rewrite our understanding of how stars are born, how black holes grow, and how the invisible scaffolding of dark matter shaped our universe. It suggests that the cosmos was not a slow and steady builder, but a frantic and brilliant artist in its youth, eager to create complexity and structure. This isn't a crisis for cosmology, but a renaissance. We are being given a new page to write in our cosmic history, and the story is far more exciting than we thought. Thank you for joining me on this peaceful exploration of the impossible. May your sleep be as deep and as full of wonder as the images Webb continues to send home. And as you drift away, I leave you with a question to ponder in your dreams. If the universe could build galaxies so quickly, what other beautiful impossibilities might be waiting for us to discover in the dark? Subscribe for more journeys into the cosmos and share your thoughts in the comments below. Sleep well.